The purpose of the experiment is to determine which of two flow plate designs, conventional hole manifolds or experimental bridges, is more efficient in a PEM fuel cell. Bridges are significantly easier to manufacture and are thus studied as a more economical alternative. Another goal is to find the humidity needed for optimal hydrogen purifier power consumption, and previous articles such as Lee's have suggested that optimal humidity will be in the higher range, around 60 to 80%, while increased airflow in the flow field of the bridge plates will increase the rate of the redox reaction and thus power output. The two designs for PEM flow plates, holes, and bridges depicted in figures 16 and 17 were placed in the fuel cell running on pure hydrogen and air and operated by a DC load drawing current from 0 to 8 amps at 0.2 amp intervals, with 10 seconds at each interval. Hydrogen and air were transported into the fuel cell at the anode, and a DC load operates the fuel cell. Exhaust air and water exits at the cathode. Data was recorded with load software, and 4 trials were done for each group. Polarization curves as well as power and voltage output graphs were created in Microsoft Excel, and a t-test was used to compare power output in PEM plate designs. The purifier was tested using a power supply and bubbler humidifier as shown in figure 15 and is depicted in this diagram. As you can see, pure hydrogen is passed through the humidifier and a humidity monitor and then introduced into the purifier, which is drawing power from a power supply. The exhaust then leaves at the anode, while the pure hydrogen exits at the cathode. This supply was used to determine how much power would be consumed at each humidity level using pure hydrogen. Data was graphed with curves of best fit on Microsoft Excel.